Sometimes people will give you a bunch of numbers like these, concentrations of solutes in the blood, and ask you to calculate something called the serum osmolality. So osmolality is referring to something like the number of moles per kilogram. Remember that if it were osmolarity, it would be moles per liter instead, but they're basically the same thing because a kilogram of water is a liter of water. But so what they mean by serum osmolality is the total number of moles of everything per kilogram in the serum. And serum, of course, is the same as plasma. In other words, they're talking about this intravascular extracellular fluid. So if I asked you how you would do that, what would you do? One thing you might be tempted to do is just to add all of these guys together, because we said that these are the four most common electrolytes. So if we add them all up, we should get a good estimation for the serum osmolality. But actually you can simplify it a little bit. So one thing you can do is say, well, I know that there's an equal number of negative and positive charges. So I can just add up the positive charges and multiply by 2, and that should account for the negative charges as well. So you could say serum osmolality is 2 times, and then the sodium concentration plus the potassium concentration. And then some people make it even easier on themselves, and they say, well, potassium concentration is pretty low, so really sodium is most of it, so I can actually just ignore the potassium. So is this it? Well, it's actually not, because here we were just talking about things that had charges. And there are actually other things in the blood that have some concentration that contribute to the osmolality, but that are not charged, and so we actually hadn't mentioned them. Now there's a lot less of them than there are of charges, and that's why we didn't mention them before, but they're still important to take into account here. So those two things are, first of all, glucose. So we want to take into account the osmolality of glucose, and then also what we call BUN. And what is BUN? It stands for blood urea nitrogen. So really it's just referring to urea, which is that waste product that we once mentioned that has 2 nitrogen atoms in it. So it has this weird name, blood urea nitrogen, but really it's just talking about the osmolality contributed by this molecule urea. Now unfortunately for sodium they give you the concentration in milliequivalents per liter, which is pretty much the same as millimoles per kilogram, but in glucose we normally get the concentration in milligrams per deciliter. So we can't just add things with different units. So to convert milligrams per deciliter to millimoles per kilogram, we need to take the glucose concentration in those units and divide it by 18. So that gives us our final equation to estimate serum osmolality. And so we estimate it as 2 times the sodium concentration plus the amount of glucose divided by 18 plus the amount of BUN divided by 2.8. Sodium should already be given in terms of milliequivalents per liter, which is like milliosms per kilogram, whereas the glucose and the BUN should be given in terms of milligrams per deciliter. And these constants will convert those values into this one.